At the very heart of quantum mechanics, there's this core idea, randomness. But what if it's all just an illusion? Today we're diving into a really wild theory called fractal resonance cognition, which suggests there might be a hidden, predictable order to the entire universe.
For more than 100 years, physics has basically told us that at the smallest, most fundamental level, the universe is all about probability and pure chance. But is that really the whole story? Could there be a deeper layer of order that we've just been missing this whole time? That's the huge question we're going to tackle.
So before we can really get into this new idea, we have to understand the giant problem it's trying to solve. And trust me, it's a puzzle that has kept physicists up at night for decades. It's called the measurement problem.
Okay, so here's the central conflict. On one hand, quantum mechanics says a particle exists in what's called a superposition. It's like a ghostly blur of all its possible locations at the exact same time. But the instant we measure it, the moment we look, bam, reality just snaps into focus. It's found in one single definite spot. So, how does it choose that spot? Why that one and not any of the others?
This right here is probably the single biggest black box in all of modern physics. This jump from a fog of possibilities to one single concrete reality is what we call wave function collapse. And the standard explanation? Well, it just says it's random. That's it. No deeper reason is offered.
But what if there's a clue buried inside all that chaos? This is where this new framework, fractal resonance cognition, enters the picture. It's a brand new theory of, you guessed it, hidden order. And this is the huge shift in thinking that FRC is proposing. What if that random choice isn't random at all? What if it's actually a predictable, deterministic process that's just being guided by some underlying structure we haven't been able to see until now? So FRC suggests that systems are guided by these things called vortex attractors. A good way to think of them is like invisible whirlpools that are constantly pulling a system toward a stable, final state. And the theory argues these attractors are fractal, which means they have repeating self-similar patterns at every single scale you look at, from the really big down to the incredibly small. Here's a really simple way to picture this. You've seen a singer hit just the right note, that perfect resonant frequency, and a wine glass shatters, right? Well, that's not a random event. It's a very specific, ordered outcome caused by a very specific vibration. FRC is basically saying something just like that is happening at the quantum level. The act of measurement creates a kind of resonance that guides the system to one single structured outcome. Okay, that sounds really cool in theory, but where's the proof? How can we actually see this hidden order in action? Let's meet the stadium billiard. It's a really famous model that physicists use to study quantum chaos. Just imagine a single particle bouncing around like crazy inside this stadium-shaped box. Its probability wave, its wave function, is famously chaotic and totally unpredictable, which makes it the absolute perfect laboratory to go hunting for some hidden order. All right, look at this. On the left, you're seeing the typical wave function pattern. It's a complex, irregular mess, exactly what standard quantum chaos theory says we should see. But now, look at the right. When a special fractal resonant potential is applied to the system, the chaos suddenly reorganizes itself into this stunningly ordered, beautiful, self-similar pattern. Do you see how the smaller clusters are perfect little copies of the larger structure? Order is literally appearing out of thin air. And this isn't just a pretty picture. We can actually put a number on this new order. Using a method called box counting, scientists calculated the fractal dimension of this pattern, and it came out to be about 1.90. This number is like a quantifiable structural fingerprint of a hidden deterministic process at work. So what in the world does a fractal pattern inside a quantum billiard have to do with solving the measurement problem? Well, as it turns out, everything. FRC proposes this exact same mechanism is what guides wave function collapse. So let's walk through how this would work. First, a system starts out in that blurry superposition of states. Then, the act of measurement creates a resonant interaction, like the singer's voice hitting the glass. This resonance then causes the system to phase lock onto one of those fractal vortex attractors we were just talking about. And just like that, the system is pulled into one single, definite, and, this is the key, deterministically chosen outcome. It's not a random jump, it's more like a guided slide into a stable state. Right. This brings us to the absolute million-dollar question. If every single measurement is predictable, guided to a specific outcome, then why is it that when we repeat the experiment thousands of times, the results perfectly line up with the probabilities that quantum mechanics has predicted for a century? And here's the brilliant answer.
While each individual event is guided to one specific outcome, the tiny, precise starting conditions are just a little bit different every single time. And that determines which of the attractors the system ends up locking onto. So over many, many experiments, the system kind of explores all the available outcomes, and the results average out to perfectly match the probabilities of the famous Born rule, the quantum rulebook for this stuff. So in this view, probability isn't some fundamental law of randomness, it's actually a statistical pattern that emerges from a much deeper deterministic process.
Now, this is a really fascinating idea, but for it to be actual science, it has to be testable, right? It needs to make predictions that are different from standard quantum mechanics. Predictions we can actually go out into the lab and try to verify. And guess what? FRC does exactly that. For instance, it predicts that if we had sensitive enough equipment, we could actually see a tiny systematic drift as the system gets pulled toward an attractor right before the final collapse happens. It also predicts that if we could measure things incredibly quickly before the system has time to fully settle, we'd see tiny little deviations from the probabilities we expect. These are real, concrete, falsifiable claims.
Take a look at this specific prediction right here. This graph shows what we expect to see from a certain experiment. That solid line, that's the standard prediction. But the dashed line is FRC's prediction. They're almost identical, but if you look really close, there's a tiny measurable gap between them. If an experiment could actually detect that tiny deviation, it would be some seriously powerful evidence for this hidden layer of reality.
And that leaves us with a pretty profound question to think about. For 100 years, we've accepted a reality that's built on pure random chance. But this theory suggests that if we just look closely enough, we might find out the universe isn't playing dice after all. Instead, it could be following a hidden, resonant, and, well, a beautifully fractal script. The search for that evidence is officially on.